Okay, this is going to be the data video for our ionic and covalent bonding conductivity experiment. So what we're going to do is this is going to be for data table number 1. Right? And so what we have right now is our conductivity setup. We have a multimeter here. Now a multimeter can measure a variety of different things like voltage or resistance or current, which is what we're going to measure. So we're going to measure this milliamps, so that's our current, and that's going to be in the units milliamps. And we've gone ahead and changed it so it's measuring the direct current, so that's what DC stands for. On here, what we have is our conductivity measure. It's 2 separate wires connected to a power supply. And so right now that circuit is broken. It means that we can't pass any electricity between these 2 wires. And so that's why our current is reading at 0. As we put different species into here, we're going to try to connect those 2 wires, and we're going to measure the current that is passed between them. So as an example, this is our deionized water. So this is going to be the same as your distilled water. That's just pure water, or as close to pure water as we can get. So just H2O. I've gone ahead and put them into this beaker. And so now we can go ahead and we can measure our current. So I generally leave this for about 10 seconds or so. And then I try to take the average value. So I can choose either the very lowest value I see or my average high one. So on this case, I might choose something like 45 because that seems to be where it's stabilized. So that's going to be our reading for our deionized water. I can go ahead and take that off. I'm going to unplug the power. I'm going to wipe it off. I'm going to put my waste beaker underneath so that way I can rinse it off with some more deionized water. Not as important with our first sample because that was also deionized water, but very important later on when we start to get other species in there. We don't want them to be contaminated. Plug it back in, and I can move on to my next sample. So this case is going to be tap water. So this is just water straight from the tap. So not clean, not purified like the deionized water is. We can go ahead and put that one in. You can see we did get a different current here, 1.4, 1.5. So I might record this as like 1.56, right? 1.56, something like that. You could do like 7 and 8 maybe, depending. You just want to try to be consistent about it. And then I can go ahead and take that off, unpower, rinse. This time I definitely want to make sure I rinse off all of that tap water. And then we can move on to our next one. Gotta plug it back in, gotta give it power. Next one I'm gonna do is gonna be our methanol. Now, the methanol that we're using, this one is going to be the liquid form of it. So that means it's pure methanol. I'm going to put that on in here. We can take that measurement and take that off. Clean. Wipe. Plug back in. We can move to our next one. Our next one is going to be methanol. But as you can see in this bottle, it's called 50% methanol aqueous. What that means is it's methanol mixed with water. We've diluted it. So instead of being just pure methanol, it's our methanol mixed with something else. And so I'm going to take that methanol here, and I'm going to go ahead and put it on. You can see I've labeled this one as methanol with the AQ on it. AQ stands for aqueous. It means that it's been dissolved with water. Put that in here. And we get our different reading. Take that off. Unplug. Rinse, wipe, move on to the next one. Our next one is glacial acetic acid. Now, glacial acetic acid is something a little bit different. Now, if you notice on it, after they have the acetic acid label, they actually have an L. It means it's a liquid. This molarity of acetic acid, the reason why they call it glacial, is it's basically pure acetic acid. It's got no water inside of it. And that's why they call it the liquid form of acetic acid. Turn back on our multimeter here. Make sure we're in DC mode. Now we can go ahead and put in our glacial acetic acid. We're going to take that off. Now, glacial acetic acid is actually quite a strong smelling acid. It smells a lot like really intense vinegar. Vinegar is like about 5% acetic acid. And so we want to make sure that we do that part either in the hood, or in this case I'm using a small amount and I'm actually dumping that right now into our waste container so we can close that up. This one is going to be our 0.1 molarity acetic acid. So this time it's our acetic acid mixed with water. And so instead of being that 17.4, we've really diluted it down. We've added in a lot of water there. Plugging this back in, taking our measurement. And you can see we get a very different conductivity. Now, with the way our current lab is set up, we're just getting like a rough estimate in some ways of our conductivities. If we wanted to get really precise readings, like say we were really measuring the conductivity of different species, and we didn't want to just try to classify them as we're going to do as high, low, or medium. Right, we're basically trying to classify them as no ions, a few ions, or many ions. What we would need to do is we would need to set up a more routine test. While I've done my best to try to limit or to keep it consistent how much material we have touching those probes, we would want to make sure that became exactly the same, and that's how we would get our most stable readings or our most consistent readings. This is going to be our sucrose. Oh, I'll show you the bottle. This is our sucrose as a solid, so that's what it means when it has a little S behind it. And so sucrose is just a type of sugar. We're measuring that conductivity right here. As you expect, not really conducting too much electricity in its solid form. Go ahead and clean that again. Put that in. And now what I've done is I've taken that sucrose and I've dissolved it in water. So I've made it aqueous, so this is the second one. We can see how that might change things. More than before, but still not great, 0.24. We're gonna see if it's just only covalent type compounds, the sucrose, which is all covalently bonded, or if it might be all solid compounds. That. Plug this back in. And so we're going to do that similar test. We're going to take our salt, NaCl. NaCl is the chemical formula for table salt, sodium chloride. This is it in its solid form. Measure that conductivity. No big change there. Gonna clean it off. You can see a little bit of that salt actually got attached, so I really want to make sure I clear that off before we move to the next part. This is the salt once again, but I've dissolved it into water. There's some solid still left over at the bottom. That's okay. It just means that there was too much salt. It couldn't all dissolve. But we're gonna just measure the conductivity of that solution. So I'm going to put it into the solution. Wow, now we have a big change there. So that was our salt that's aqueous. the solution version of salt, AQ afterwards. You want to make sure you get those in the right place. If it's got an S afterwards, that's just when it's a solid. If it's AQ, that means it's a mixture. And that means that it's mixed with water in this case. And so we use our deionized water. We're not going to do the mercury chloride, so the 0.1 HgCl2. We're not going to do that test. Mercury is actually a little bit hazardous to work with, and so we're not going to keep that in the lab because of the waste that it creates. I'm going to plug this back in. Instead, what we're going to do is we're going to jump down to the next one. We're going to do our HCl. So this is hydrochloric acid, 0.1 molarity hydrochloric acid. So similar to our acetic acid in its concentration when we did the solution. So we get that conductivity there. I'm going to go ahead and rinse these off. And we're going to do our last test. Our last test is going to be our sodium hydroxide, 0.1 molarity sodium hydroxide. I'm going to go ahead and plug this in. Take out that 0.1 molarity sodium hydroxide, put that on in there. Get our conductivity there. It's actually kind of interesting. When we are putting them in, you can actually see some little bubbles that show up. We see that with the table salt solution, right? We see it with, so that's the NaCl aqueous. We see those bubbles show up with the HCl solution, the aqueous acetic acid solution, and the NaOH. We can actually see little bubbles forming, and that's because what's going on is what this box is doing is it's trying to pass some voltage between these two probes. And when enough current gets passed, we can actually see the bubbles form as it splits that water into hydrogen and oxygen. And so that's what those little bubbles are that you can see. It's hard to see on the video, but that's what you would see in person. And so that's all we need for table number 1. So we have our conductivities. Now what you want to do is you want to classify them as whether they had no ions, a few ions, or many ions. And so it's up to you to kind of make that decision about where you might classify things as many, where you might classify them as a few, and where you might classify them as no ions, right? So look at your values and try to categorize them into those 3 points. You can kind of see if you see any trends that develop with that.